This lecture is entitled TCPIP part 1. So, in this module 2 we would be covering the topics in 3 lectures. Here we would be mainly talking about the TCPIP protocols. In fact, TCPIP is not a single protocol, it is a suite or a family of protocols. We would be looking at some of the important members of this family. But first let us try to understand what TCPIP is and how it has evolved over a period of time. Okay. So, talking about the internet, TCPIP is a protocol which, well, you can say it started as early as in the 1970s and it got very quickly accepted by a wide community of users. In fact, when the internet came into the being, TCP/IP was the prime vehicle which was used to connect the computers in the internet and to allow them to communicate over the network. Using TCP/IP, the computers were able to communicate among each other, and also another very important thing, they were able to share some resources across the network. Some of the resources like disk space or some of the expensive equipments were expensive in those days, and over the network it was possible to share those resources. And work on TCP/IP started in the late 60s, and in the early 70s it started to take shape. Now in US, like most of the innovative developments, the initial research on TCP was funded by the US Department of Defense, the military. So, as part of their project, it started off with a very small network. It was called ARPA. It was called Advanced Research Project Agency, ARPA, and the network which evolved in the process, it slowly came to know as the ARPANET or the ARPA network. Okay. So, this ARPANET was the first network, you can say, which started to use the first version of TCP. Okay. Fine. Now, this TCP has become so widely accepted technology in modern internet that you can say that in today's world, the internet as we see, this is entirely dependent or based on the TCP/IP technology which lies under it. So, in the internet, TCP/IP today is treated as a standard. Standard means, say, when you buy or purchase a new computer, and if you want it to get connected to the internet, the first thing you must ensure that your computer learns or understands the language of TCP/IP, because this is important, because all other computers which are connected to the internet, they know and understand TCP/IP. So, if your computer can talk in the same language, then you can communicate with the others. But suppose you have a computer which have a proprietary system, it uses something other than TCP, then it will not be possible for your computer to send a message or communicate with some other computer which is connected to the internet somewhere else. Okay. So, this TCP/IP is a standard. It has been used to bridge the gap between non-compatible platforms. Well, when we say non-compatible platforms, what I mean to say is that some of the machines you are trying to connect may be running the Windows operating systems, some may be running some version of Unix, Linux, some may be Macintosh machines, Macs. So, there are a wide variety of types of machines and operating systems which are in use today. So, if all of them have a common layer of software, namely the TCP/IP, then using that common layer they can very easily talk among themselves and work in, you can say, synchronism with each other. So, the most important point to note is that all computers connected to the internet today must understand TCP/IP. This is important. Okay. Fine. TCP/IP, as I said, this is not a single protocol, this is a family of protocols. And you recall earlier we had mentioned about the International Standard Organization's 7-layer reference model, which is known as the OSI model. Now, this OSI model, as I had mentioned, this had evolved through a consortium of a number of user groups. They had identified the different functionalities of the network software, and they tried to find out that what are the basic functionalities and the relationships. If we can separate them out into layers, then the development of the networking software may become much easier. So, analyzing the requirement and the interaction and the functionalities of the different levels of network usage, they identified 7 different layers in the hierarchy. Now, as this standard body was developing the 7-layer architecture, internet sitting on top of TCP/IP has already started to grow and evolve. Okay. So, larger and larger number of users, they started to use internet, they started to get familiar with TCP/IP, and TCP/IP you can say was a part and parcel of their daily activity or work. So, even though the 7-layer OSI model was a very well thought of model, it had a very sound logical basis of this layering, but TCP/IP, which is not based on such a strong logical base, but it attracted a much larger user community because there was an application, namely the internet, which was in place, and it had some very interesting properties, and it started to grow very rapidly. Okay. So, TCP/IP became much more acceptable to the user community. So, the truth today is that although the 7-layer model may be a better way of carrying out the layering, but in reality most of the protocols which are in use today, they are based on TCP/IP, which is not a 7-layer model. In fact, TCP/IP follows a simplified form of the 7-layer model. You can identify 4 layers in this model. Okay. Now, let us see how this modeling is carried out. But first, let us try to have a look again at the purpose of layering. Well, we develop software in terms of layers because number 1 is that if we make some change in one of the layers, as long as the interfaces remain the same, the other layers need not be modified. So, if the interface remains the same, we can make changes to a layer pretty easily. This is of course one reason. The second reason is that if we have well defined layers, your total software can be defined into well defined modules. So, the software development process also becomes much easier. Okay. Now, just to recall, the OSI 7-layer model had these 7 layers starting from the lowest level: physical, data link, network, transport, session, presentation and application. Now, you recall one thing, suppose you have a network like this, there are several nodes connected, right. These are several network nodes connected and there are some links which are joining them. Suppose this is my source and this is my destination. I want to send some message from this source to this destination, from this source to this destination. Now, there are some of the layers, in fact the lower 3 layers, physical, data link and network, they work on a point to point link, means they work or they cooperate in sending the data over this link and so on. Whereas, the higher 4 layers, for them the intermediate thing is more like a black box. Only the 2 end systems are important, and whatever this source is sending, as if the destination is receiving directly. This is the advantage you have in layering. The lower 3 layers of the software, these are working on the point to point links, but they ensure that the packets which are starting from S will finally reach D. In contrast, the higher 4 layers, they are not worried about how the packets are delivered to D, they are more worried about what is reaching D finally. These are therefore called host to host layers, because for them the internal network is a black box. Only the 2 communicating entities at the 2 ends, the source and the destination, they are important, as if the source is directly talking to the destination. Okay? Fine. Now, in TCP/IP, the simplified 4 layer model which is used, well, if you draw an analogy from the OSI model, approximately the layering would look like this. At the lowest level, this is sometimes called the data link layer. This layer will be responsible for the transmission of frames over link. But one thing you understand, although the lower level link is called the data link layer, this must also include the physical layer. Now, the reason they are put together in a single block or layer is that in most of the modern systems, what happens is that we have a so called network interface card or a NIC, which we put inside our computer, and through a networking cable we connect that NIC. Okay. Now, that NIC, that piece of hardware, it works both as a physical layer and as the data link layer. So, both the 2 layers get embedded into the hardware interface card. That is why we really cannot distinguish the 2 layers in modern day systems. That is why they are often embedded into a single layer. Now, the next higher layer, the network layer, this is responsible for packet delivery across the internet. A source sends a packet, it is the network layer in all the intermediate nodes as well as the source and destination. It will be responsible for routing or forwarding the packet systematically from the source to the destination along the correct path. Transport layer is the end to end link, where the source and destination can talk directly. An application is any program which can run on top of these. Now, examples of applications may be electronic mail, email, maybe any other program you are running which is communicating with any other client server program, in fact, which is communicating with another program on the other machine, they can be treated as application. Okay. Now, in a 4 layer model, let us look into this diagram in a slightly more detail. Now, what we are showing here is that there are 3 nodes A, B and C. Suppose A is the source, C is the destination, and the packets or the data from A go to C via an intermediate node B. Okay. So, when I say that A is the source and C is the destination, I mean is that on machine A there is some application program which is running. Similarly, on machine C there is some other application which is running, which will be receiving the data sent by the application running on A. So, what the application program running on machine A will do is that it will send some information down to the transport layer. transport layer will be sending it down to the network layer. Network layer will take some decision that it will be looking at the destination address, the address where the packet has to be delivered, and in case this node A has more than one outgoing links, it will take the decision through which outgoing link the packet has to be forwarded. So, the network layer will be sending back the information to the data link layer corresponding to the selected link. For example, I have selected this link. So, over this physical link, the data packets or the frames will go to machine B. Machine B is not the final destination. Now, here again there can be several outgoing links. So, what this machine B will do, it will again send back the packet to its network layer, and the network layer will again take a decision depending on the destination address that over which link we have to forward it. Suppose it selects this link. So, now from the network layer it again comes down to the data link of that corresponding selected link. So, finally, the packet reaches C. So, from C again it traces the reverse route, data link to network, network to transport, and transport back to the application. So, the point to note is that in all the intermediate nodes, only the network layers up to the network layer, data link and network, these two layers are coming into the picture. Only it is at the two ends where the end to end layers like transport and application are being used. So, this diagram shows that how typically data flows in a 4 layer model, network model. Okay. So, now let us come to TCP/IP specifically, what the TCP/IP suite of protocols really mean. Now, as I had mentioned, TCP/IP does not refer to a single protocol or a few 2 or 3 protocols. In fact, this refers to a family of protocols. All these protocols are built on top of a so called connectionless technology. Now, connectionless technology, as we had seen earlier, this means datagrams. There is a basic mechanism of transporting datagrams over the network. So, in TCP/IP, the basic idea is that data will be sent from one node to the next as a sequence of datagrams. Now, exactly the way datagrams work, each datagram is independent of the others. So, the datagrams will be sent independently. Okay. Now, again it is a characteristic of datagrams, since they are sent independently, there is no guarantee that the datagrams that comprise of the same message will be following the same path. Say suppose I have a message, I break up the message into 5 datagrams and I send them independently. Each of these 5 datagrams may be following different paths. Okay? So, they may be reaching the destination following different paths, and accordingly the order of arrival may be different. Some of the datagrams may get lost in transit, and if there is some error checking, timeout, retransmission, then some duplicate datagrams may also get generated. So, variable delay, arrival order, destination are possible. Okay. Now, let us have a very quick look at the important members of the TCP/IP family. This diagram summarizes the different important family members in TCP/IP. Of course, at the lower level we have the data link and the hardware layers. This refers to the network interface card, as I told you. Typically we use Ethernet at this level. At the next higher level, this is the network layer level. In TCP/IP, the protocol that works at the network layer level is called Internet Protocol, or in short IP. So, IP is the main protocol which is working at the network layer level, but in addition there are several auxiliary protocols like Internet Control Message Protocol, Group Message Protocol, Address Resolution Protocol and Reverse Address Resolution Protocol, which also works at the network layer level, but they have specific functions. Like ICMP is used to generate and send some error messages. Like for example, address resolution protocol is used to translate from an IP address into an Ethernet address, for example. So, IGMP and RARP also has some specific purposes, but in a typical application you will be using Internet protocol. These protocols are typically hidden from the applications. These are invoked and used in a transparent way. As a user you will not be able to see that they are being used, or as a programmer also you will not be using them directly. Okay. Now, at the transport layer level you have two options. You can either use transmission control protocol or TCP, or you can use user datagram protocol or UDP. So, you see, although we call it TCPIP, actually you can also use UDP and IP. Okay. TCPIP is just a name for this family. Moving up to the application layer level. So, at the application layer level there are a number of well defined applications, only a few of them I have listed here. We have file transfer protocol, we have trivial file transfer protocol, we have simple mail transfer protocol, you have simple network management protocol, domain name server, or you can have any general user application which has been developed. Okay. This is only a short list. In general you can have any number of applications at this level. So, typically an application running on this level, for example, this user process, this can interact with either TCP or UDP depending on what you want. TCP or UDP in turn will interact with IP, and IP will interact with the lowest layer. Okay. This diagram shows that simplified typical data flow model. This is the typical scenario where at the application layer level the user processes, they will be using either TCP or UDP. Okay. There is a choice, there is a characteristic. They will in turn be using IP, and IP will be interacting with the lowest layer. So, the most important members of the TCP/IP family are TCP, UDP and IP, these three. So, first let us try to see briefly what the basic functionalities of these three models are. First let us look at IP, the protocol that works at the network layer level. As I had mentioned that a network layer protocol is responsible for the correct routing of a packet from the source to the destination. So, it will take some decision that where to forward or send the packet next, and the packet will find its way from the source to the destination, taking help of the IP layer software that is running on each of the intermediate nodes. Okay. Basically, IP is a transport system for datagrams. So, at the level of IP, it is only datagrams which flow on the network. So, IP is basically a datagram packet delivery system. It is responsible for routing the packets, of course. Moreover, if it sees that a packet is too large, it cannot be handled by a network, then it can break a packet into smaller pieces which are called fragments, which we will be talking about later, that how this is done. So, a packet may be broken up into smaller fragments or packets, which later will need to be reassembled again to get back the original packet. Now, this reassembly is done at the final destination. Okay. But the point to note is that IP does not do any kind of error control. It is an unreliable service. It is basically a datagram service, and all the unreliability that comes with datagram, it stays with IP also. Like a packet may get lost, packets may arrive out of order because the individual packets may follow different paths through the network, and in case of timeout and retransmission, duplicate copies of the same packet may be flowing through the network. So, the final destination, the IP layer at the final destination has to manage all these things, packets arriving out of order, some packets not coming at all, and multiple copies of the same packet coming. Okay. So, these issues have to be handled there. Now, looking at TCP, which works at the transport layer level, and you recall the transport layer level is a end-to-end protocol where the two hosts which are running on the two machines, they talk to each other. TCP is a reliable transport layer protocol. Well, when we say reliable, what we mean is that it is a connection oriented reliable service. When we say connection oriented, well, the user or the user application gets an illusion that there is a connection which has been established between the two end systems. So, the application program running on one computer believes that a connection has been established with the application running on the other end system, and I can send some message directly to the other machine. But what happens in practice is that ultimately the data will be transported by the IP layer below, and IP is an unreliable layer. So, TCP has to do some additional error checking, and in case of an error, TCP will have to recover from the error. So, TCP will give an illusion to the layers above it that well, everything below you is a very reliable network. Okay. So, essentially the tasks which are performed by TCP is that splitting a message into packets, reassembling the packet at the destination again, and it checks if some of the packets are missing. So, if they are missing, an explicit request is sent back to resend the packets, and in this way reliability is ensured. And TCP sits on top of IP. So, the way it interfaces is that the packets which TCP generates will be forwarded to IP individually for delivery, but IP does not do any error checking or error control. So, all error control is the responsibility of TCP. Okay. So, this in a nutshell is what the TCP layer is supposed to do. And the user datagram protocol UDP, that is also a transport level protocol, but that is different. Well, as compared to TCP, TCP tries to provide reliability, it tries to provide a connection oriented service, but UDP does not try to do anything. UDP says that well, I am trying to transport a packet as fast as I can, I am not concerned about reliability, I am not concerned about in which order the packets are going. I will try to impose a minimum amount of overhead, I will try to deliver the packet fast. This is the philosophy behind UDP. So, UDP provides a connectionless service, like there is no apparent connection that is set up between the source and the destination. This is an unreliable service because it does not do any explicit error checking or error control. The applications which prefer to use UDP are those for which messages are small enough which can be fit into a single packet. A typical example is the query that is sent out by the domain name system. DNS query is an example of such a message. In fact, DNS uses UDP for that purpose. Because the protocol is much simpler, you do not have to establish a connection, do not have to maintain a history of the packet, so that if a packet gets lost, you can send back a request for retransmission. So, since you are not doing all these bookkeepings, this protocol is much simpler in comparison. This is simpler as well as faster as compared to TCP. So, since it is simpler, it will never split a data into multiple packets. It is expecting that the packet will be of a size which can fit into a single datagram, and it does not care at all about error control. Interface with IP is very simple. Each UDP packet is a datagram, it simply forwards it to IP for delivery. Okay. So, interface with IP is also very simple here. Okay. Now, there is another issue. Well, if you have another look at this TCP/IP stack, just showing the important protocols TCP, UDP and IP. Broadly, there are 3 layers, if you recall: the physical and the data link layer, the network layer and the transport layer. Talking about the addresses, in each of these 3 layers, there are 3 different addresses which are used. At the lowest layer, just assuming the lowest layer is an Ethernet, here you use something called the physical address of the interface link. In this case, this will be a so called Ethernet address, and this is a 48-bit address. This 48-bit Ethernet address is embedded inside the network interface card which you plug into your computer. So, it is that card which has a hardware address built into it, that is the Ethernet address. So, when a frame finally comes to your computer, it must come with the Ethernet address as part of the packet or frame. Okay. But when you are looking at the network layer, it is a 32-bit IP address which is used to identify the computers in the internet. Now, this 32-bit IP address is allocated and assigned in a much more systematic way. This is a logical address, no computer comes with that address built in. You can program a computer, you can assign any IP address to it. Okay. Now, the purpose of this assigning of IP address is that you are trying to make it easier for the intermediate nodes in the network to forward and route packets just by looking at the IP addresses. But once the packet enters or comes into the LAN where the final destination node is situated, so there you have to finally find out the Ethernet address of the destination. That is done through that ARP protocol I talked about a little while ago. So, using ARP you get the Ethernet address, and finally the packet will reach the final destination addressed by the 48-bit Ethernet address. Now, at the level of the transport layer, now you recall the transport layer is an end-to-end layer. So, here 2 applications on 2 end hosts are communicating. Well, here also there is an address called port address, it is a 16-bit wide address. Now, let us see why this is required or needed. Now, at the transport layer level, when there are 2 end hosts and 2 applications running there are trying to communicate, it may be very much possible that on each of these machines there is not only one application, but several applications running. That is the typical scenario in most computer systems today. There is time sharing, there is multitasking. So, there are many programs which are running at the same time. So, you must mention that when you are sending a message to exactly to which application program at the other machine you are trying to send the message. So, this port number in essence identifies an application which is running on the particular machine. Okay. This is why we have a hierarchy of addresses. Physical address to ultimately identify the machine through its hardware interface card. This IP address in order to identify the network where the machine belongs, and finally to send or route the packet to that network, and the port address to identify an application running on the end machine, end host. Okay. Now, any layering of software, this networking software, all of them have some sort of layering. We talked about the 7-layer OSI model. Now, we are talking about the 4-layer TCP/IP model. Now, when there is layering, the packets flow in a systematic way from top to bottom and again from bottom to top. Now, as this information flows up and down, some additional information gets appended or are removed during this movement. Now, let us see what this means and why this is done. Now, this addition of this information as a packet moves along the hierarchy is called encapsulation. So, let us look at this issue of encapsulation now. When some information or data flows down the protocol hierarchy from the top to the bottom, some information gets added to it. These are some additional information. This additional information are in the form of headers and possibly trailers. So, you have the original message or data, you add some more information to it and send it to the lower layer. Similarly, the lower layer will add some more information to it and put it to the next lower layer. So, in this way it goes on, but when it reaches the other side, the flow of data is reversed, data moves up the hierarchy now. Now, as it moves up, these headers and trailers which were appended, they get removed systematically one after the other. Now, here let us try to illustrate with the help of an example. Let us take an example of an application layer protocol, a simple application layer protocol called trivial file transfer protocol. Well, for those of you who are already familiar with the file transfer protocol, just let me tell you that this TFTP is a simpler version of the FTP protocol, which uses UDP for delivery of the data. So, TFTP is a simpler version of FTP. Okay. So, we assume that the TFTP client is trying to transfer 200 bytes of data, and this TFTP protocol, this appends a header which is of size 4 bytes. So, with this information, let us see how this encapsulation takes place. First, we will look at the 4-layer protocol diagram: Ethernet, IP, UDP, and at the application layer level, on one side you have the TFTP client and the other side you have the TFTP server. So, first when the data is being sent, the data will slowly move down the hierarchy from TFTP to UDP to IP, then to Ethernet, then it will actually flow through the physical link, and on the other side it will be flowing up the hierarchy. So, as it moves down, the headers and trailers will get added, and as it moves up, the headers and trailers will get removed. Okay. So, here in this example, let us see. So, as I had mentioned, TFTP runs on top of UDP. Okay. Let us see how the headers and trailers are appended. So, in this diagram, we are just showing how the headers and trailers are getting appended. Okay. So, well, when we say appended, if we look back at the previous diagram, so we are actually talking that when the message is moving down the hierarchy. So, when it moves up the hierarchy, exactly the reverse process will take place, the headers and trailers will get removed. Okay. Fine. So, this is the data which we are trying to send. Now, this data was 200 bytes long. First, the data gets encapsulated as a TFTP message. The TFTP protocol appends a 4 bytes of header to the data to produce a message packet. This header will be required by the TFTP protocol or the server running on the receiving end, because the receiving end will be looking at this data and will be deciding what to do with this. Fine. Now, this message packet then gets forwarded to UDP for delivery. So, the UDP protocol also appends a header out here. This is a 8 bytes of header. So, UDP header is of size 8 bytes. Similarly, UDP will be sending this packet to IP for delivery. So, IP will again be adding a header. Now, for an IP, the minimum header size is 20. I am assuming minimum, it is 20. Finally, for the physical delivery of the packet, it has to be sent down to the Ethernet layer, and Ethernet layer appends both a header of size 14 bytes and a trailer of size 4 bytes. So, here you see that we were trying to send a data of 200 bytes, but ultimately if we add these numbers up, it becomes 250. So, in order to send 200 bytes, actually we are sending 250 bytes over the network. These additional 50 bytes constitute the overhead. Now, this is a characteristic of any transmission or communication that we attempt over the net. So, whatever we send, there will be some additional overhead that you have to take care of. So, this encapsulation example shows you that how this encapsulation adds some headers and trailers, and this leads to additional overhead in the packets. Okay. Fine. Now, let us look at a slightly more detailed look at the IP datagrams, at the IP protocol. As I said that IP protocol takes a packet from the TCP or UDP layer and it appends a header, as the example we just showed, and it sends it down to the Ethernet layer. So, first let us try to understand what kind of header the IP layer puts in, what are the contents of the header and their purpose. Okay. Let us try to understand that first. So, first, just to recall, we had mentioned it briefly earlier, IP layer provides a connectionless and unreliable delivery system for packets. This we have already mentioned before. Since this is a datagram delivery service, each packet is independent of the other, and since they are independent, IP layer need not maintain any history of the packets. Each packet is sent individually. Now, since no history is maintained, each packet must contain the source and the destination addresses, because this is very much similar to the way you post a letter. So, a letter is posted as an individual entity. So, unless you post the complete destination address there, your letter will not reach, and if you want an acknowledgement back, you also have to put your own address. Okay. So, source and destination addresses are required in this kind of a scenario. Fine. And since IP layer is a datagram based service, error checking is not done, it does not guarantee delivery of packets. So, if you need to do any error checking, it must be done at the higher layer. IP does not do any error checking, it simply attempts to forward the packet through the correct route. It can fail, a packet may get lost. This IP does not report any error if such a thing happens, or it also does not try to recover from that error. Okay. And the way IP layer does the encapsulation is that it receives a data chunk, this we had seen in that example, from the higher layer, it can be TCP or UDP. It adds a header to it, as we had said that the minimum header size is 20 bytes, and this 20 bytes will contain all the relevant information which will be needed for routing and flow control. Okay. So, now let us see what this encapsulation means. Diagrammatically this means this, we have the data and the IP layer will add this 20 bytes header to the data to form a so called IP packet. So, this is the so called datagram which will get delivered. It takes the data from the higher layer TCP or UDP. This data will be coming from either TCP or UDP, and this 20 bytes minimum header will be appended to it and this datagram will be created. Okay. This diagram shows you the syntax of the IP header. In the previous diagram we have showed a data and the header part. Here the data part is out here, this section is the data. Remaining portion constitutes the header. Now, in this diagram, well, every row corresponds to 32 bits or 4 bytes. If you look at the first 5 rows of this diagram, these are essential information, and what we have mentioned here as options, these are optional items. So, if there are some optional items, the header size may become more, but minimum there are 5 rows, which means 20 bytes. Now, let us look what are the fields. We will be explaining the purpose of these fields one by one. Var means version, this is the header length, service type, total length, identification, flags, fragment offset, time to live, protocol, some kind of header checksum, and source and destination IP addresses. These are the information which are present in the IP header. Now, let us see what this means. Okay. Version is a 4-bit field. This indicates that which version of the IP protocol you are using. Most of us today use version 4. Of course, IP version 6 has already been standardized and it will be becoming more popular very soon, but still today the most popular version of IP protocol is the version 4. So, the first field will contain the number 4 in binary. The second field, the header length, this is also 4 bits. This field indicates the length of the header expressed as the number of rows in the diagram or 32-bit words. Minimum size is 5, which means 5 into 4, 20 bytes. In 4 bits, maximum number can be 15. So, including header, including the options, the total IP header size can be 15 into 4 or 60 bytes. Okay. The third field is the total length, which is a 16 bits field. This indicates the total length of the datagram in bytes including the headers. Since it is 16 bits, the maximum datagram size can be 2 to the power 16 or 65536 so many bytes. So, this field will give you an upper limit to the size of the datagram. Well, service type is a field which is not really used universally. So, using this you can allow packets to be assigned a priority, but you can have this feature provided the intermediate nodes or the routers can interpret this field and can give higher means it can give higher priority to some of the packets as compared to the others. But normally in very few installations we have this kind of a scenario. So, this field is typically unused. There is another field called time to live. This is a 8 bits field. This is an interesting field. See, in IP routing, as I said, the IP layer will forward a packet from one node to the other. Now, the IP layer at each node will take a decision where to forward it next, but suppose due to some reason the information that is available to some IP layer somewhere is wrong. So, instead of routing in the correct path, it is routing through the wrong path. So, it is possible that a packet may go on circulating in a loop and this may go on indefinitely. Now, in order to control this, you do not really you really do not want this to happen. So, the time to live prevents a packet from travelling in a loop. The way it works is that the senders of the packet will set a value and store it in this field. This value will get decremented at each hop. Hop means from one node to the other, as it moves on, the value gets decremented. As soon as the value reaches 0, the packet is discarded. So, depending on the value the sender has set, the maximum time the packet can stay gets limited. The protocol field indicates that which higher level protocol was being used, TCP or IDP, they have some specific values. Similarly, the IP header field, the source IP address, the destination IP address, this we will be looking at more detail later. These are all 32-bit fields. There is identification, flags and fragment offset. These are used for handling so called fragmentation. This also we will be discussing later. Options is used if you need or if it is supported by the routers again. Well, one feature that you can use using options field is source routing, where the source of the packet can tell that which path the packet needs to follow. So, instead of leaving the decision up to the intermediate routers, the source can take that decision. And finally, the header checksum, there is a checksum which is computed only on the IP header, and the way it is computed is that the header is treated as a sequence of 16-bit integers. These integers are added using 1's complement arithmetic, and 1's complement of the final sum is taken as the checksum value. So, if the checksum mismatch is found, the datagram is simply discarded. No attempt to correct the error is made. Okay? So, whether the datagram is correct or not, that is made. So, with this we come to the end of this particular lecture, lecture number 3. So, now let us have a look at the solutions to the problems which we had given in our last lecture, lecture number 2. Let us quickly browse through this. The first question was, with respect to speed of data transfer, which of LAN or WAN is faster? Undoubtedly it is LAN, because in LAN you can have speeds which can range up to 1 gigabits per second or more, but in WAN it is much less. What is the typical speed of a modern Ethernet backbone LAN? Backbone LANs are faster. Typically we have 1 Gbps, or in some modern installations it has gone up to 10 Gbps even. Okay. Why is circuit switching not suitable for computer to computer traffic? Because the computer traffic is bursty in nature, and in circuit switching you are establishing a dedicated connection, and for bursty traffic you will be not be utilizing the link at all times. So, link utilization will be very poor. What are the 3 steps that are required for data communication using circuit switching? Well, first you have to establish the connection, then transfer the data, and finally the connection has to be closed. With respect to sharing of links, which of circuit switching or packet switching is more suitable? Because circuit switching some of the links may be dedicated, but in packet switching none of them are. So, packet switching is more suitable in this respect. Among virtual circuit and datagram, which approach requires less information in the header? Obviously, virtual circuit, this we will see later also, because in a virtual circuit the connection is already established, but in a datagram each packet must contain the source and destination address. Okay. Which of virtual circuit datagram makes better utilization of the links? Datagram, because datagrams may follow different paths and the links may be better utilized. 8th, which of these two guarantees ordered delivery of packets in the absence of any errors? Datagram does not guarantee ordered delivery because packets may follow different paths. but in virtual circuit the TCP layer will allow ordered delivery of packets. Under what circumstances the datagram method of packet delivery prove useful? Small messages, less errors, reliable network. 5 packets, well 5 means few, needs to be sent from host A to another host B. Which of virtual circuit or datagram would be faster? Datagram, because you need not have to do any initial circuit or connection establishment, okay. That overhead is removed. For a 4 kilobytes packet sent over a 10 Mbps link, what is the transmission time? Well, this is easy to calculate. 5 kilobytes means 5k into 8 bits, divide by 10 megabits, it is 4 milliseconds. A 600 byte packet is sent over a 20 kbps link whose propagation delay is 10 milliseconds. After how much delay the packet will reach the destination? Well, in this calculation you will first take the propagation time plus the packet transmission time. The total comes to 250 milliseconds. Which layer in the OSI model are host to host layers? This you know, transport, session, presentation, application. These are host to host or end to end layers. What is the responsibility of the network layer in the OSI model? To route packets from one node to another. This is the main responsibility on the way to its final destination. 15. What is the responsibility of the data link layer? To ensure reliable data transmission over point to point links. Okay. Typically the unit of data transmission is frames. What is the basic difference between a bridge and a router? Bridge will connect LANs, while router can connect WANs to LANs or other WANs. Bridge works at the data link layer level, while router work at the network layer level. Okay. Now some questions from today's classes. In today's class, how many bits are there in the IP address? How many bits are there in the Ethernet address? What does the Ethernet address signify? What does the IP address signify? What does the port number signify? What does the various layers in the simplified TCPIP protocol stack correspond to with respect to the OSI 7 layer model? Why is the transport layer called end to end or host to host layer? IP is unreliable and TCP uses IP. How does TCP provide reliable service to the application layer? List 2 common applications that use UDP. Why is the IP protocol considered unreliable? What does TCP do if the message to be sent is larger than what a single datagram can handle? If a 1000 byte data message is sent using TFTP, what will be the size in bytes of the corresponding Ethernet packet? I mean after encapsulation. What are the minimum and maximum header sizes of an IP packet? What is the purpose of the time to live field in the IP header? If the IP header is 192 bytes long, what will be the value of the HLN field? What is the maximum size of data that can be accommodated in an IP datagram? So, with this we come to the end of today's lecture. Thank you.